Hello, everyone, and welcome. Please join me in welcoming Dr. Malena Rice, newly Ph.D. recipient in astronomy from Yale University. Malena is actively engaged in postdoctoral research as a 51 Pegasi B Fellow at MIT. Malena will describe for us the latest observational and computer applications in detecting planetary and interstellar bodies, which are believed to reside in the outer regions of our solar system. Please give a big welcome to Malena.
Thank you. And I'm going to share my screen and start my slides and just ask, can everyone see this? Does that look right?
Yeah, we're good.
Awesome. Thank you for the great introduction. I am actually just missing this is the 1 year that I'm not in Connecticut because I'm returning next year as an assistant professor, which I'm really excited about. But I'm just taking a little bit of time out in Boston right now. So I have a lot of different facets of my research program that I am going to try to touch upon, kind of following three main themes that I think are some of the really exciting directions that really planetary science in general is going in, a couple of kind of case studies of really interesting things that are being studied and that I'm specifically looking at as well. So I'll try to touch upon both the things that I'm doing as well as broader in the field, what is happening. And really the goal of my research is to try to understand planetary systems very broadly. So this is a big task to tackle. It's sort of understanding, how do planets form? How do they evolve? How do we put together all of these different pieces? So hopefully this will be kind of a nice overview of some of the highlights that I have been looking at. So I wanted to start off by just grounding us with the known exoplanets. This plot was made like 2 months ago, but has changed very little since then. So this is just showing as a function of orbital period, which is effectively how long is a year on this planet versus the mass of the planet in Earth masses, just all of the planets that we found so far. And you can see all the solar system planets that are shown with their names also on this plot and where they fall relative to all the planets around other stars. So all these gray points are planets found around stars other than the sun. There are over 5,000 at this point and counting. There are many more that are being found all of the time, which is fantastic. And you can see that, well, there are a couple of features that come up. First of all, there are sort of these three clumps that pop up. So there are these different classes of planets that we start to see emerge, and we're actually sensitive to generally the planets that are in between these gaps. So this is kind of an indication that these are actually real clumps of planets that are more common, and maybe there are some others that are less common in between. So the first clump here is the hot Jupiters, which are around about 1% of stars. These are giant planets that are orbiting really, really close to their host star. So they're extremely hot, very strange chemistry. They have like vanadium oxide and titanium oxide and all these crazy chemicals that don't really exist on Earth because you don't get such high temperatures naturally, at least here. And you get those all the time on hot Jupiter. So their atmospheres are very strange, and they are we know of a lot of them because they're the easiest ones to study, but they're not actually that common. So 1% of stars is not particularly common. Then we have the super Earths and sub-Neptunes. These appear to be around about half of all stars. So these actually seem like they're probably the most common of the types of planets that we've seen so far, which is kind of strange because we don't have one in the solar system. As you can see, all the solar system planets are kind of off to the right here. And we don't have a super Earth or a sub-Neptune that we can study up close right now. So I'll talk about maybe our prospects a little bit later. But that's kind of interesting. These seem to be very, very common, but we don't have one in the solar system. And then we also have our cold Jupiters. So these are sort of more similar to our Jupiter that we know and love. These are farther away from their star. They're not getting as much insolation, so they're not kind of being attacked by this really heavy flux of photons all the time. And they're a little bit more like the Jupiter that we actually have within our own solar system. But then something that's really interesting about this whole parameter space is that we really haven't seen much that looks like the solar system planets just yet in these extrasolar systems. So we sort of have two different pieces of our puzzle here, where we know the solar system, which is one very, very detailed version of a planetary system that is quite unlike the other ones that we've seen. And then we have all of these very low resolution planetary systems that are very far away. We don't know very much about them, except maybe a couple of the planet sizes and where they are in the sky. And that's about it. And we have thousands of them versus our one detailed solar system. So putting those together, kind of the goal of a lot of the work that I have been thinking about is trying to figure out, is our solar system unique? And is this telling us that the solar system is very unlike other planetary systems out there? Or is it just that maybe we have detection biases where we can't see all these planets? We already know that some of these solar system type planets are harder to find than a lot of the ones that we've seen before. So I mentioned hot Jupiters are the easiest ones to find, even though they're pretty rare. But we still don't really have a good handle on the answer to this question. And so I'll talk a little bit more about how we're approaching that and what we can do to try to answer this. And when I say that I want to study this with a synthesized view, I really mean that it's important to consider not just the planets, but also every component of your system. So when we have a planetary system, that usually includes a couple of ingredients. You've got a star, you've got your planets, and you've also got a lot of minor planets. You've got lots of asteroids, comets, and everything in betweens. And just generally, we would call them minor planets as anything that's sort of smaller than a planet. And so I really aim to draw a connection between these and to try to use them each to sort of cohesively understand what these planetary systems are telling us, both when we look at our own solar system, which is what I'll sort of start this talk with, and then also when we look at extrasolar systems. There are three key, again, components that I want to focus on today. And these are sort of guided by three questions. Where I'll first start off by talking a little bit about Planet 9, which is something that drives a lot of my research. And in particular, the question associated with this is there a ninth planet in the solar system? There's been one that has been colloquially called Planet 9 that has been proposed. And does that exist? Because we've never actually seen it before. So I want to start off with the evidence for why people think that this planet might exist, and then talk about how we're actually going about trying to look for it. So this is just a figure that shows all of the very, very distant extreme trans-Neptunian objects in the outer solar system. So here, just to give you a sense of the scale, you can see a 250 AU scale bar, which is 1 AU is the Earth-Sun distance, an astronomical unit. And this red circle is roughly what all of the kind of colloquially well-known stuff in the solar system falls within. So all the solar system planets are within this red circle in the middle, as well as the Kuiper belt. All of that is within that little red dot. And what we're looking at is the orbits of these very, very distant asteroids, where the only reason we can actually see them is because they're on these extremely eccentric, elongated orbits. And so we can actually detect them when they are at their closest point to the sun. So there are some that you can see are getting kind of close to the outer edge of the red circle, and that's where we can see them. But if they were out on their farthest end of their orbit, there's no way we would be able to find them with current technology. So there are all of these what are called extreme trans-Neptunian objects on these very eccentric orbits in the outer solar system. And there are a few things that are weird about these. First of all, it's kind of weird that they're on these orbits at all, because usually most of the stuff in the solar system falls on pretty circular orbits. And if they don't fall in circular orbits, we think that it's usually because of interactions with the known planets. So Jupiter is very good at kind of ejecting or nearly ejecting material such that you might end up with these other asteroids. So a population of centaurs is kind of a well-known one, where they end up on these really kind of strange orbits that are more elongated. They might be misaligned with the rest of the solar system. But all of these objects that we're looking at here are too far away from Jupiter for it to have actually caused them to be on these strange orbits. So it's really strange that they're so elongated, even though they're so far outside the solar system, that they're not really interacting with the solar system planets at all. And it's not really clear how they got to these orbits. Another thing that's weird, and that is kind of cited as the main evidence for Planet 9, is that the long-term stable asteroids in the extreme trans-Neptunian object population appear to be preferentially clustered on one side of the sky and also in one plane of the sky. So what I mean by that is looking at just these purple orbits, where if you put these all into a numerical integrator and you say, what's going to happen to all of these asteroids over time? Some of them will be unstable. So some of them might be on chaotic orbits. They might get thrown out of the system, their orbits will change over time. Some of them are metastable. So depending on your initial conditions, they might be more or less stable. And some of them are just stable and they don't change at all. And those are the ones that are all pretty much clustered on one side of the sky, or the ones that are stable. And that's kind of strange because your orbits should actually spread out over time. The fact that we live in a solar system with multiple planets is the main reason for this. So when you think about an orbit, that works really well on a short time scale, that you just have a star and an orbit and you can figure out where your object is going to be within, the coming years at least. But over very long time scales, like 1 billion years or so, those orbits don't actually close perfectly and they start to sort of precess around the center of mass of the system. The reason for this is because when we define an orbit, we assume a very simple two-body system. So we say there's the sun, there's this object, and we're defining its orbit relative to the sun. But you also have all of these other gravitational perturbations from particularly Jupiter is the main one, but from all the other mass in the solar system that is affecting everything else. And so because you have these extra perturbations, your orbits never close perfectly and they end up sort of spreading out across the sky. So these should have spread out within about 1 billion years. The solar system is about 4.6 billion years old. And so unless something is holding them in place, it's kind of strange that they would all sort of be just on one side of the sky. And then in addition to being on one side of the sky, they appear to be roughly in the same plane. So it's hard to see from a 2D image. But if you sort of looked at all these orbits, they actually would, if you kind of turned these orbits, look like they're roughly in the same plane. So everything in the solar system, you can kind of think of it as falling on a plate where all of the solar system planets are kind of rolling around this plate and they're pretty much in just this nice 2D plane. And you don't have like Jupiter orbiting sideways relative to Earth or anything like that. Everything is pretty flat. Whereas these orbits also are pretty flat, although they're not in the same plane as the rest of the solar system. So just to give a sense for the scale here, again, 1 astronomical unit is the distance between the Earth and the Sun. The solar system is about 30 AU in size. And if we zoom way out, the planet 9 that is predicted by this hypothesis would be about this far away if you sort of just scale the sizes. So it'd be 300 to 800 astronomical units away. And the idea is that you would have this planet that's kind of on the other side of the sky, or its orbit is on the other side of the sky from all of these other asteroids. And it would be able to provide this restoring torque that's needed to force all of those orbits to stay in one place. So if Planet 9 exists, then it would be about 5 to 10 Earth masses in size, which is, and this is something that is backed out of orbital models looking at, if you put all of the solar system into these simulators and see what's going to happen in the future, and then you try out different versions of Planet 9, then you can actually force all of these orbits to be confined to a particular space in the sky. And this is the type of Planet 9 that actually is able to do that. And what's really cool about that is this Planet 9 would be exactly the kind of super Earth sub-Neptune type planet that is really common in extrasolar systems and that we don't have in the solar system. So this, if it exists, is a really amazing opportunity to maybe be able to someday study one of those planets up close and actually figure out, these are so common in other planetary systems, but we can't study them in detail because they're too far away. And if we had our own solar system, maybe we would be able to do that. Okay, but should we have not found this already if it exists? Well, it turns out, and this is something that always seems to surprise people because, we study the cosmic microwave background and we study the Big Bang and all of these like really, really very distant things. And yet we still aren't sure how many planets are in the solar system. That's absolutely crazy that we still don't know that. But it turns out that there actually is a space where you could just be hiding planets. You could be hiding tens of planets, maybe not like 100 planets, but you could certainly fit a few of them out there. And the region of space is shown in gray here, where if you had a planet that was at the right distance and the right mass, so the same right distance away from Earth, and that was in the right mass range, we wouldn't have expected to see it yet. So the limits of this box are just defined by existing surveys as well as kind of our definitions for planets. So a planet, if we're just looking at the mass axis, if we want to define it as a planet, it has to be massive enough that it's clearing its orbit. And that's kind of what defines what a dwarf planet is, where Pluto, Eris, Sedna, and the other Sedna is actually an extreme trans-Neptunian object, but it's considered a dwarf planet. Those are the objects that are kind of planet-like, but they're a little bit too small to clear their orbits. The planets that are too big, we would have already seen. So you can sort of rule out with our existing surveys, we definitely don't have planets that are over 100 times as massive as Earth. They would have to be smaller than that. The ones that would be too nearby, we should have already seen the gravitational effects of. So again, every time we see a new planet, it's going to perturb everything else in the solar system. So it has to be far enough away that it fits all of our models. We very precisely know, especially where certain spacecraft are, because we need to communicate with them. That is known to very, very high precision. So you can track that over decades, and this has to be consistent with those error bars that you get from tracking all of your spacecraft. And it also has to be close enough that it wouldn't have been tossed out of the solar system in its birth cluster. So stars, we think, usually form in stellar nurseries, and there are usually a lot of stars nearby when they first form. So if your planet's too far away, then it probably would have been thrown out of the system very early on. And it turns out that this Planet 9 that was predicted falls right in the middle of this space. So it is exactly the kind of planet that you would have expected to not have found because it's so far away, and it's just the right like mass that you would need to not have been able to see it yet. So there are a couple of surveys that have looked for Planet 9. I'm going to focus on one that I am leading because that's the one that I know the most about, and a lot of the ones that are ongoing haven't necessarily published a lot of what they have done. So there are individual efforts sort of using telescopes and just scanning blindly across the sky and saying, we're going to just search lots of different areas, see if we can try to pick out a planet. So the most common way to do this is by taking an image of a part of the sky, returning to it a few hours later, and then blinking between the two images to see if you find a moving object. So this is how Pluto was found. And I'm doing this with a kind of larger scale computational survey that is trying to get around that and is trying to do it more efficiently and with a lot more computer like computational cost as opposed to sort of human cost of clicking back and forth. It did take Clyde Tombaugh a pretty long time to find Pluto. So the data set that I'm using is called it's from the Transiting Exoplanet Survey satellite. So TESS was mentioned earlier. And this is actually, the TESS team is the team that I work with at MIT, and I was actually at a conference for this satellite and everything that it does over the past 2 days. And this is a spacecraft that was designed to look for extrasolar planets around bright nearby stars. You can see its survey strategy that is being swept out here in this animation. So the spacecraft first observed the southern hemisphere, and it observes each of these regions of the sky with its 4 cameras for about a month at a time. And then it turns around and it flips and it observes the northern sky. This gap in between the northern and southern is the ecliptic plane. So that's where all the solar system planets lie. That's where all the zodiac constellations are. It's where the solar system is. And it is basically just looking at the entire sky, which is really convenient if you're looking for a planet and you don't know where it is. So while it was designed to look for extrasolar planets, it actually turns out to be a really fantastic survey that you can also use to try to look for something like Planet 9, because you have a month of data in almost every part of the sky. And these gaps that exist in especially the ecliptic plane have actually been filled in over time. So within the next couple of years, TESS is actually going to reach 100% completeness over the entire sky. Right now, I think it's at about 80%, maybe 90%. And so it actually has gone back and it's continuing to observe and will continue to do so indefinitely at this point. So the TESS primary mission ended up covering these areas that you can see here in color. So the animation was slightly off in that there were a few sectors of data that were kind of moved northward. So you can see 14 through 26 here were all shifted upwards, and that's just because there's too much scattered light from the moon, and it was expected that it wouldn't be as bad as it was when the spacecraft actually got up in the sky. So they decided to shift these sectors so that they're not capturing the areas of the sky with as much moonlight, and so that they are better able to utilize the data that is coming from the spacecraft and will return to those regions when they don't have the moon shining in them quite so badly. So there are a couple of lines on this that might be very familiar to you, but in case they are not, there is the galactic plane is one important line that's shown here. So this is where the Milky Way is in the sky, and that's where there are a lot of stars. There's the ecliptic plane, that's where the solar system is. So they are not aligned with each other. And then I also wanted to briefly show the extended mission has filled in a lot of this ecliptic plane region, which is pretty important for solar system science. And so if you just pull out the sectors that are most relevant for the Planet 9 search, you can see them sort of overlapping with the highest probability regions of the sky for Planet 9 here. So in red, those are the areas that we think Planet 9 is really likely to be in. And you can see the TESS data set kind of overlaid onto it, where it actually matches up pretty nicely, where there aren't a lot of parts of this high likelihood region that are not observed by TESS. And all of these regions that are shown here have already been observed, and this data is already available. So if Planet 9 exists, it is really kind of just a matter of efficiency of searching for it. And so this is something that I've been working on, just building a pipeline to do. And in order to do that, you need to actually utilize the entire month's worth of data. So you can't see something this dim in a single image. Planet 9 would be around in V magnitude about 19 to 21, which is, it's a pretty dim rock, or maybe not rock. It might have a gas envelope. It certainly probably would have a gas envelope, but it's pretty dim. It's not giving off its own light. It's just reflected sunlight, and it's very far. So the sunlight has to get to the planet and has to reflect all the way back to us. So in order to find it, we need to actually combine a lot of data from many, many weeks, and ideally the entire month of data. But something cool that I showed you we're able to do is by stacking together these frames along the paths of these objects, we can actually pull out these extremely dim signals. So this is just showing Each row is a different object that has been recovered by my algorithm, where on the left, we're showing just if you shift and add together all the images after subtracting away the stars, getting rid of a lot of systematics, and just add together all of these fluxes along the path of your object, you can pull out a really nice signal, especially for the relatively bright ones. But we think Planet 9 would be about as bright as the top row here. So that's pretty promising because that's a really nicely detected signal. And then if you do a blind search, which is the middle and right column, then we actually also could pull out the signal. And so what you do here is you actually just consider, okay, well, I want to look for any objects between 70 AU and 800 AU. So that is very, very far in the distant solar system. You're just looking at kind of anything out there. And just shift and stack those images along any possible orbital paths and just keep the highest flux that you get along any path, and then just look for what looks like the best signal out of all of this. And it turns out that we can actually really nicely recover these pretty dim objects when you actually just take all of this data from the test mission and from this month's worth of data. So to sort of ground this a little bit more, I have a video of the shift stacking recovery of Sedna, which is this dim extreme trans-Neptunian object that was shown in the top row earlier. And in the left here, you can see with all the stars masked out, just one of the regions that TESS is looking at with some asteroids that are passing through. And on the right, you can see just adding together all of these images. We're sort of shifting them to the left and adding them together. So we start with a big blank space in the left region of the right panel, and it gets filled in over time as we add more and more frames together. So this super dim object called Sedna, that's shown here, it's not at all obvious in these frames to the left, and you can't see it in any individual frames. You can only see it when you add together hundreds of frames. And so that's really the goal of what we're trying to do to search for Planet 9, is to add together lots and lots of frames to actually pull out this really dim signal. We have a lot of diagnostics for candidates. So we can inject candidates and see what we're able to recover. These are just kind of cuts through the fluxes when we are injecting a few candidates. So this in particular shows four different, well, there are four injections in this image that these figures were pulled from. So there are four peaks in the Y pixel plot. And the main thing here is really just that we are pulling a few different things that we're using to make sure that this actually looks like a real object. The flux needs to accumulate consistently as you're adding together frames, because you can get false positives from getting stray starlight and getting stray asteroids that are in the foreground that weren't properly masked out. So this is an ongoing search, but it is currently, I think, one of the more promising ones to find something like Planet 9, or potentially even something that's not like Planet 9, which could be pretty cool as well. So there is other evidence for potentially a Mars-sized planet in the outer solar system. And the idea there is that there is actually a small warp in the mean plane of the Kuiper belt, where it's not just flat. There's actually a small warp that is in this kind of region of asteroids in the outer solar system. And it's been shown that that can be very well reproduced if you have a Mars-sized planet that is out beyond the Kuiper belt, and that we also wouldn't have been able to see yet. So this search is really looking for not just Planet 9, but really anything that would be relatively bright that's out in the outer solar system. And it'll help us to actually get closer to being able to definitively answer that question of just how many planets do we have in our solar system. Okay, so that is Planet 9. And next I want to move on to interstellar objects, which is another really, really interesting group of objects that have only recently become attainable. And I want to talk a little bit about what interstellar objects can teach us about planetary systems. So there have been two of these that have been found so far, which are Oumuamua, found in 2017, and Tuai Borisov, Borisov, I think. It's a Russian person, Russian actually amateur astronomer found this interstellar object with a telescope that he built by himself, which is pretty remarkable. And there have only been two found, 2017 and 2019. Still to date, we haven't found any more, which may or may not have had to do with maybe some telescopes were shut down from the pandemic. Maybe they're just not as common as people might have thought. And something that's really interesting about these two objects is that they're incredibly different. So Oumuamua looks nothing like Borisov and vice versa. They're very, very different objects, but these are really probably the material that is being used to build extrasolar planetary systems that's just being thrown at us. And so that's amazing. We have never really been able to see anything like that up close before. We can't go to other stars and collect samples because they're just too far away for us to be able to feasibly do it. We have limits from the speed of light, limits how fast we can actually go other places. And so the fact that these planetary systems are throwing the stuff that makes them at us is really a gift, and there's a lot that we can learn from this. So Oumuamua was the first interstellar interloper, and it was a huge mystery. You've probably heard a lot about the controversy related to Oumuamua, and a lot of the media actually sort of publicized it as looking like this kind of elongated cigar-shaped thing, but it turns out that it's just about as well fit, if not a little bit better fit, by sort of a pancake-like shape. So it looks like Oumuamua probably was sort of a very flattened pancake-like asteroid that in some ways looked sort of like a solar system asteroid, but in other ways it did not. So first of all, the dimensions were very strange, and that's something that was pulled out from the light curve. So you can see how the light that we get from the object is changing over time, and it has these pretty enormous modulations that are telling us that it needs to have either a very non-uniform color. So if you have an albedo that's very, very bright on one side and very absorbent on the other side, then you could get very large oscillations in the light that you get as it's tumbling. Or probably more likely, if you assume it's just made of one general composition, it's probably just this really strange pancake-like shape. And in addition to that, it looked like it was sort of accelerating out of the solar system, which is not well understood. It's possible that it was outgassing some material, but the gases that are pretty common for solar system comets to be outgassing were not detected in any detectable quantity coming out of this object. So there have been all these ideas that maybe it was a block of hydrogen ice or of nitrogen ice or something really strange that has never been seen in the solar system before. And it's a real mystery because it is never going to be observed again. Like, this is an object that came through the solar system, it left, and we're never going to be able to see it up close again. But we may be able to see other objects like it if we're able to find more of these interstellar objects with time, which it looks pretty promising that we should be able to detect more with upcoming observatories. Borisov, this second confirmed interstellar object, was completely the opposite story, where it looks just like a solar system comet. So it was on this very clearly hyperbolic orbit. So you can see that from the eccentricity being higher than 1. That means that it's not bound to the solar system. It enters, it's leaving, and it's not coming back. And Borisov, it's the same color as solar system comets. It has the same compositions as solar system comets. And it really looks very similar to the material in our solar system. So in a way, that's kind of reassuring, because if everything in extrasolar systems looked like Oumuamua, then maybe we really would be alone. But the fact that, you know, there are at least some other extrasolar systems out there that probably are made up of similar material like that of the solar system is kind of reassuring that, oh, okay, our models are making sense. The solar system is made of normal material that is also the same as what we're seeing in at least some extrasolar systems. And maybe there are some strange things out there that are happening sometimes that we still don't understand. And that's kind of the excitement about interstellar objects, is that we still don't really know just yet. Besides studying them directly, these interstellar objects can also tell us more about the planets that are in extrasolar systems. So these probably, again, are the building blocks of extrasolar systems that were ejected early in the planetary system's lifetime. So when the solar system was formed, it's thought that 10 to 30 Earth masses of material were probably tossed out by Jupiter at some point. So Jupiter is very effective at tossing out material that comes close to it and is interacting with it gravitationally, because it is able to push those asteroids very easily to above their escape velocity that they need to get to escape the solar system. Most of the extrasolar planets that are known are actually much closer into their host star than Jupiter is to the sun. And so they're actually really bad at ejecting planetesimals or small rocky bodies. And that's just because everything is very tightly bound when you're very close to the star. And so it's hard to push material above the escape velocity. And most of these planets are very, very inefficient at it. So what that's telling us is really that if these interstellar objects are as common as is suggested by the fact that we've seen a few of them, if we have seen a couple of them and they were as big as the ones that we saw, that indicates there probably are more of them out there that are smaller. Then that suggests that there are some extrasolar planets that are at wider separation that maybe are ejecting them. And it turns out that there actually is other complementary evidence that is showing this. In particular, these are 20 images of protoplanetary disks that were imaged by the Atacama Large Millimeter Array through the disk substructures at High Angular Resolution Project, DSHARP. So these are the nurseries of extrasolar planets. These are where they're being born. They are sort of forming within these disks. And there are a lot of different interesting features that show up in these disks. You can see like some of them almost have these weird spirals, and there are all these really, really interesting dream structures that we were never able to resolve before just a couple of years ago. And in particular, the most common feature that has been observed is that there are a lot of these axisymmetric rings and gaps. And those don't have to correspond to planets. So you can get that from anything that can create a pressure bump in your disk, but it's thought that a lot of them probably do correspond to planets that are carving out gaps within the disks. And there's been complementary evidence that has come up showing that there's actually kind of a change in the velocity of the gas right at the location of the gap in some cases, that's suggesting that there's actually something that is moving and that's pushing the gas so that it's not following the same track as everything else within the disk. So, and that's only in some cases, so not all of these are necessarily planets, but we think that some of these probably are. And if you run hydrodynamical simulations and forward model these particular systems, knowing their masses, knowing how much gas is in them, trying to reproduce these images from kind of first principles, then you can show that it's actually consistent with Neptune-sized planets, if there are lots and lots of Neptunes that are out there in the outskirts of planetary systems. And those are the kinds of planets that are really hard for us to detect right now. So planets that are close into their star are pretty easy to detect. Planets that are far away and very massive are easy to detect. But then there are all the things that are sort of in between, like the ones that are far away and a little bit less massive, like Neptune, are hard to see when they're more aged. But this is probing a kind of different region of space. This is also looking at very young planets potentially, showing that it appears that there is evidence for a lot of these Neptune-sized planets that are kind of actual Neptune analogs that are far out from the host star, that are at the distant edges of their planetary systems. And if those Neptunes are there, then they're also really good at populating things like the population of interstellar objects. So if you have all of these Neptunes, then they are very capable of tossing this planetesimal material, all of these rocks that are surrounding them, out of the system. And we know that amidst all of the gas that we're seeing within these images, they're also is expected to be a lot of dust that is being used to actually accrete and create these planets early on. So within the stage, it's a messy process where some of the material will accrete to become planets, some of it will be thrown out of the system. And it looks like these pieces are sort of fitting together where these planets are forming with lots of Neptune-sized planets in the outer regions of these systems. And some of it is accreted onto the planet, some of it is thrown out, and it populates these interstellar objects, backgrounds of just rocks that are floating around throughout the galaxy at this point. And our solar system just kind of is passing through this background density of these floating rocks that are around, and we happen to see them pass through sometimes. So this, if you actually do assume that this is where the interstellar objects come from, which is not 100% clear, but this is one of the more natural ways that you can explain the interstellar objects that we've seen, then it looks like we should actually be seeing a lot of these with the Vera Rubin Observatory. So probably at least a few a year, if not many, many more. And this is a pretty poorly constrained problem because we've only seen 2 of them so far. So it's hard to say exactly how common they are. But if you assume they follow a power law distribution of sizes, which is what the minor planets in the solar system follow, and if you assume that they're similar to the solar system in certain ways, then you can extrapolate that we should actually find a lot of them in the coming years. And the Vera Rubin Observatory should be operational. I think it's starting, what year is it? 2022. So it should be science operational in early 2024. So that's when we can expect potentially a lot of results from interstellar objects, which is really exciting. And there have been plans through the European Space Agency to sort of think about, if we do find interstellar objects, how can we send a rocket there? How can we get a sample return and actually study it even more up close than from just taking images and spectra. So that's a really exciting future direction as well. Okay, so that's the interstellar objects section. And then I want to talk about exoplanets, and there is a lot that goes into this. So I'm going to try to touch upon as much as I can, but certainly won't be able to touch upon everything ever in exoplanet science. But this is really one of the really big sort of driving questions of a lot of people, and in particular my field of looking at the junction of astrophysics and planetary science, which is, why is there such a tremendous diversity of exoplanets, and why don't they all look like the solar system? Why are there so many strange exoplanets out there that we really don't understand well? And the story of all of exoplanets, it really does begin much longer ago than just the last couple of decades when we found the first exoplanets. There have been searches for exoplanets for many decades. But we found the first one in 1995, and then they slowly started accumulating after. And we've really started to be able to explore this question more with the Kepler mission. So the Kepler mission was launched in 2019, 2009, much longer ago. And it was searching for planets that are just around stars in one particular part of the sky. So the footprint of the Kepler mission was, if you take your fist and put it at arm's length, that's about as much of the sky as the Kepler mission was looking at. And it just stared, and it just looked to see if it could find planets in that particular part of the sky. So there's this one field of the sky that has tons of known planets around it. And then we're slowly starting to fill in the rest of the sky as well. So Kepler was pretty amazing for showing us this incredible, again, diversity of planets. So we had found a couple of kind of strange, mostly hot Jupiters before this, but Kepler was really what brought us to finding thousands of planets, and in particular, planets in multi-planet systems and around lots of different kinds of stars. So what we're seeing here is the Kepler orrery, and this is just showing a small fraction of the Kepler systems. There are many, many more of them, where at the center of each of these circles is a star. And you're just seeing the planets that orbit around lots of these different systems to scale with the solar system. And really what I think this is showing is just how different these systems are from the solar system, where these are all very, very compact systems where your planets are orbiting extremely close to the host stars. And we've got these enormous planets orbiting really close in. We've got sort of multi-planet systems with Jupiter type analogs, as well as smaller planets that are kind of orbiting right next to their host star. And there is a tremendous range of temperatures of these planets, of sizes, of kind of orbital properties. So this is just showing them all on circular orbits, but there have been very interesting, extreme, eccentric orbits as well. And so it's really amazing. It's really at this point a question of what kinds of planets don't exist, because it seems like as we're filling in more parameter space, like any sort of planet imaginable seems to pretty much have been found at this point. So this is just showing kind of a sense of how many of these transit events are occurring, where again, this is the Kepler cameras that are taking up that fist size on the sky. And you can just see what was detected within just a single week with Kepler, which was really absolutely revolutionary for exoplanet science. And what Kepler was looking for, just for a reminder of how these planets are usually found, and for the reason that we have such bad detection biases, is that it was looking for when a planet is passing in front of its star and it blocks out some of the light. And so you get a little bit of a dip in brightness. So your probability of seeing a transit, so having the right orbital geometry, it goes down very dramatically as you get wider and wider orbits. So we end up really biased towards very short period planets. And that's not necessarily the worst thing, because these types of planets are also the best ones to characterize in other ways, which I'll also mention a little bit later on in more detail. But that's just the reason that we end up seeing a lot of a certain type of planet and not necessarily as many of the ones in the solar system, because even Mercury is on a wide enough orbit that its likelihood of transiting from any viewpoint of some alien system off in space is very, very low. So I'm going to skip that because we have talked about TESS already, but the goal of TESS, well, maybe I'll play it again just for the sake of talking about TESS a little bit, because I love TESS. But the goal of TESS really was not as a Planet 9 mission. It was used to find more of these exoplanets. And the idea there was really that Kepler was just staring at that one field in the sky, whereas TESS is filling in all of the planets all across the sky. Kepler stared at that one field for 2 years, whereas TESS is only looking for about a month at a time. So TESS is really most sensitive to the bright stars, where you can see a lot of events over these kind of short time scales, where you don't need to have as much accumulated flux from a really long time. So if you're looking at dim stars, it's kind of hard to find a planet unless you stare for a very long time and stack many transit events. But TESS is great for finding all the nearby planets. And that's great, because if we want to understand the chemistry of any of these planets, if we want to study their atmospheres, if we want to be able to actually get spectra, so this is just showing kind of you take a transit event and you can get a spectrum during the transit and actually subtract off the starlight and figure out what the actual composition of that planet is. Or at least its atmosphere. So it's a little bit tougher to get bulk compositions, but you can figure out, at least at the atmospheric layer, what the planets are made of, if they're showing any interesting features. And so TESS is really kind of pushing this effort to search for something that's more like Earth, these kind of rockier planets where we can actually characterize and see, are there any possible biosignatures? Are there ways that we could check if these are actually something that could be habitable, or even if they're not habitable, what does that tell us about, how the solar system planets look in context relative to all of these other planets that we've observed? And so there have been all these really, really beautiful pictures through the James Webb Space Telescope, but actually what exoplanet astronomers are most excited about is the spectra. And I think that's actually true for a lot of astronomers. But the exoplanets, like, you don't really get a lot of pictures of exoplanets, unfortunately. We wish that we could get more of them. And I'll show a video of like one of the only sort of pictures of exoplanets that we have. But once you get something like the James Webb Space Telescope, you get these incredible spectra that tell you in such great detail exactly what those planets are actually made of. And in fact, they're in such great detail that a lot of them haven't been released yet because James Webb is very new, but there have been these remarkable results from just a couple of systems so far that are so detailed that our models just can't fit them. Like, they're just not detailed enough. We have too many simplifications in them. So that's actually a really exciting thing, is that we're able to see all of these different features that are really pushing our theory, and that we need to now step up to and say, okay, well, there's a lot of stuff in here that we need to figure out what it actually means. So this is really going to be a big revolution in exoplanet science and understanding compositions, as well as just where all the planets are and how many there are. And then the last thing that I sort of wanted to talk about with regard to exoplanets is also the orbital geometries of these planets, because we sort of talked about, you know, there are lots of these strange planets that are very close to their stars, lots of different masses, lots of different compositions, but it turns out they also have a lot of really weird orbits. So in the solar system, the sun's equator is pretty well aligned with the plane in which all the solar system planets lie. So the star is spinning in one direction and all the planets are orbiting in the same direction that our sun is spinning. But in exoplanet systems, that's not always the case. You end up with a lot of planets that are really not aligned at all. Sometimes they're even going backwards. So here the planet's going the other way relative to the star. And sometimes you get planets that, like, one of them is going sideways, one of them is going in the right directions or prograde in the same direction as the stellar equator. And that's a really interesting mystery where we don't entirely understand what caused this. And it probably has something to do with the dynamical evolution of these systems, but we don't yet really understand exactly what it means. So we'll talk about a few different theories for what could have caused these different kind of lopsided orbits that have been observed. The way that this is observed is using something called the Rossiter-McLaughlin effect. And so the idea here is that a star is spinning. And so if you take radial velocity observations across it, so you're looking at the integrated velocity of the star relative to your line of sight, the planet's going to block out first the blue shifted part of the star. So as it's spinning, there's a side that is spinning towards you that has blue shifted light, and a side that's spinning away from you that has red shifted light. And as the planet passes over, it will first block out the blue side, and then it'll block out the red side. And you can actually see that as a warp in the net velocity that you measure. So if you take a look at either a prograde planet, which is on the left, or a not prograde planet, which is in the middle or the right, you get very different signals from the velocities of your star, where if you have a planet that's just moving in the same direction as the stellar equator, you get a nice symmetric signal where it covers up the blue side, then it covers up the middle, then it covers up the red side. But if it's orbiting sideways or in a different direction, then you're going to get a weird sort of distorted signal, as shown in the middle or the right. So a lot of the work that I've been doing recently has been doing these observations and trying to understand what causes planets to be put on these strange orbits. So I use mostly the Keck 1 telescope, which is one of these two. I never really know which one it is, but one of them's Keck 1 and one of them's Keck 2. One of you might actually know which of them. Sorry, go ahead.
It's the left one.
It's the left one. Yeah, so I have never actually been up the mountain, unfortunately. I've been to Keck headquarters, but haven't had a chance to go up. But yeah, this is on Mauna Kea. These are the biggest operational telescopes in the world right now. So they're 10 meters in diameter. And they're really great for looking at these really tiny signals from things like exoplanets, especially. And they're able to, something like this Rossiter-McLaughlin effect, you have to get a really good signal across a single transit event. So you really need to have these enormous telescopes that can collect a giant number of photons in order to see something like that. So a couple of the ways that we think planets might get these strange orbits, you could either have a star fly by, or something that causes the disk itself to be misaligned. So when planets form, they come from disks, and you can actually misalign the disk earlier on. We've seen some misaligned disks in extrasolar systems, or disks with warps and all these weird structures, as we saw earlier. So it's possible that you could just misalign the disk and have a planet form in a misaligned system that's already kind of thrown off. You could instead have multiple planets in the system. They interact. One of them might eject the other and be launched onto a really eccentric orbit and spiral in. So that's one possible other way that you could get these misaligned systems. Or you could have, in a three-body system, these star planet with three different bodies interactions that can, it could either be a stellar flyby, or it could be a third body that is bound in the system that is leading to these oscillations in the orbital properties that then cause it to end up being misaligned. And all of these are specifically usually thought about in the framework of hot Jupiter formation. And that's because most of these misaligned systems that we've seen so far have been hot Jupiters. That's not 100% true at this point, where some of them have been Neptune-sized planets, where some of them have also been shown to be misaligned. But mostly we see this for hot Jupiters simply because they're the easiest ones to observe again. So just to put names on what each of these are, you could either have star disk interactions and then quiescent formation in a misaligned disk. So nothing violent is happening to the planets once they formed. They just stay in the same places that they originally were in. You would expect circular orbits. You could have high eccentricity migration. So one planet gets launched to a super eccentric orbit, and then it spirals inwards through tidal interactions with its host star. Or you could have high eccentricity migration launched by a companion star. So there are lots of different ways that you might be able to get your kind of weird misaligned hot Jupiters. So I'll sort of flash a few different results from these Rossiter-McLaughlin observations, where this is the first one. This is for the stellar obliquities and long period exoplanet system survey that I've been leading, that's been looking at wider orbiting planets that don't have strong star-planet interactions, so they are thought to kind of form differently from hot Jupiter. So we're trying to see, do the same trends kind of spread to other planets when you look at them as well. So you can see on the left just a transit of this planet. So it creates a dip in the light from its star. In the middle is its radial velocity amplitude, so the wobble that it produces in its host star, as well as the best fitting model that has kind of a little blip in it. So you can see it around phase 0. And then the blip is kind of fit by all of these very densely observed points that we got with the Keck telescope, specifically with the high-res spectrometer on the Keck telescope. There are a couple of other observations we've done. This one was with both Keck high-res spectrograph and another telescope that is in, I should know where this is. It's in Arizona. There was actually recently the Contreras fire that shut down this telescope for a little while, and it's still not operational for a little bit longer, but hopefully it'll be back up soon. But this observation was taken back in 2021 prior to that fire, and we were able to show that this is an aligned system. The earlier one was aligned. This is another aligned system, and most recently we found another aligned system. So it looks like a lot of these systems are aligned, but not all of them. So the main trends that have come out are multi-planet systems. So if you have more than one planet that is known to orbit the star, they're usually aligned. That's not always true. So we have two at the bottom that are these kind of weird outliers where the black line is showing the stellar spin axis, and that's relative to the plane of the planets. That's just shown horizontally here. And there are a couple of these stars that actually just have planets that are orbiting. HD 3167 has polar planets, which is pretty interesting, where they're actually orbiting sideways relative to the stellar spin. And K2290 is relatively retrograde, actually, which is interesting, where the planets are going backwards. But all the other all the other multi-planet systems are pretty close to alignment with just going around the stellar equator. So that probably means that they form in a not super dramatic way. They form within their nice orbits within the protoplanetary disk, and nothing very dramatic ever happens to them, except in these lower two systems where you might have had one of these has a companion star that probably helps to flip the system. And the other one, it might have had to undergo these planet-planet interactions that can sort of scatter your planets onto different orbits. Another thing that we noticed is that warm Jupiters around single stars tend to be aligned. So this is showing the misalignment, which 0 degrees is perfectly aligned versus 180 degrees is it's orbiting backwards, 90 degrees is polar. And on the left, we can see hot Jupiters in purple, and we can see warm Jupiters in, I guess it's more of a pinkish color here, as well as most of these yellow points are warm Jupiters. Those are just the ones in my survey that I showed a little bit earlier. And it looks like pretty much all the warm Jupiters are aligned with the host star, but the hot Jupiters are not. They're kind of all over the place. So this is telling us that those two different populations of planets, the wider orbiting ones and the closer in ones, probably formed in very different ways, where the ones that are very close in may have undergone some dramatic migration mechanism, like the high eccentricity migration that I mentioned earlier, that would have thrown them onto these misaligned orbits at some point, whereas the warm Jupiters formed again in a very gentle way, where they may have never been disrupted by companion planets. Something else I wanted to note is that this lambda measurement it's an angle that's projected onto the sky. So it's not a perfect measurement of the exact misalignment, because there's a third angle that isn't quite measured through lambda. But if there are some systems where you can actually get this third dimension, if you can figure out how fast the star is rotating by measuring its star spots. And so for the hot Jupiters that have actually had those measurements, you get this 3D angle instead of the projected angle. So the 3D angle is psi here. And what's really interesting that has come out of that is that the hot Jupiters seem to be in these two populations where they're either orbiting forwards or they're orbiting sideways on these polar orbits, where they are orbiting kind of perpendicular to the equator of the star. So that's really strange. That's not well explained right now. And this is something that a lot of astronomers are kind of scratching their heads about and trying to figure out why this is, or if this is just due to some kind of observational bias or a bias in the way that the data was reduced. So that, I think, is going to, if we figure out that's real, that's going to be a really big, useful indicator for how did these systems get to these polar orbits, and what does that mean? What does that tell us about how these systems are evolving? And then last, I wanted to briefly talk about the non-transiting exoplanets, because again, there are a lot of them that are not perfectly moving in front of their host stars. And this is just going to be kind of a brief discussion, because a lot of the science that's being done now is for the transiting ones. But for the ones that don't transit, you can also directly image them. So this is actually a survey that I have worked on in the past, called the Gemini Planet Imager, which is on Gemini South. It's actually being moved to Hawaii pretty soon, I think, but Gemini South is in Chile. And this has been used to create these pretty spectacular images of exoplanets that are very, very far from their host star. So this is the one exception to earlier I said, oh, we can't really take pictures of exoplanets. But it turns out that if your planets are massive enough and if they're far enough from your host star, then you actually can. So this is a real video of exoplanets orbiting around their host star with a coronagraph blocking out the starlight. This was made by a good friend of mine who is actually my first ever astronomy TA as an undergrad. And this is just a really amazing video that it's gotten a lot of attention, so you may have seen this before, but I think there's actually now a second video that has been made of a different system, and there are no other systems that we have videos like this for. So this is really unique and something really special that we actually are able to get these beautiful videos and images of any of our exoplanets. And then it's not only exoplanets that we can see. So we saw protoplanetary disks earlier that we can get through these kind of millimeter wavelength observations with these radio telescopes in Chile. But with GPI, we can also get these nice coronagraphic images of debris disks, and these are sort of like the Kuiper belt, but scaled up about 100 times in mass. And most of them that we see are actually edge-on, like what we're seeing in these images. This is a particular debris disk that I worked on for a while called Ph.D. 32297, where you block out the star, and then usually you're most able to see the edge-on ones because then you're able to integrate over all the dust in your line of sight, and there is a lot more that's being added up to add to your signal if it's edge-on. So this is just a gallery of all the different debris disks that have been observed with the GPI instrument. And so we've seen a lot of these. These are older. So the protoplanetary disks we saw before are where planets are born, whereas these are more of just disks that exist perhaps alongside planets. Some of these systems might have no planets and they might just have a lot of dust, which is also kind of an open question of why didn't they form planets? Why did they just have a lot of dust in them instead? And that's not something that is very well understood. The Nancy Grace Roman telescope is planned for launch in roughly 2027. And one of the really cool ideas for this, which I think is still kind of being considered, but it's not entirely clear whether this will happen, but it would be amazing if it does, is this idea of using a star shade where you have a telescope that also has an external shade that is launched alongside it. It has these nice petals to get rid of diffraction patterns that you get from your starlight. So if you design your coronagraph not as a circle, but instead as a nice flower, then you're able to get rid of diffraction effects much better. And then you might be able to just directly image a lot of these extrasolar planets, particularly if you're looking in space and you don't have to deal with complications from the atmosphere of the Earth, which is the main limiting factor for our ground-based versions of this, all the other direct imaging telescopes. But in addition to this, we'll also have these really, really enormous telescopes like the extremely large telescope in Europe and potentially the 30-meter telescope also in the United States that will also be enormous and will be able to give us much better images directly of these extrasolar planets, whether or not they're transiting, which opens up a whole other realm of these planets that we're not able to see just yet. So that wraps up the last section on exoplanets. So I just want to thank you all for listening, and I'm happy to talk more, to take any questions. Hopefully this was kind of an interesting overview of what I think are some of the most exciting things in our field right now. I'm definitely biased as a planet person. I didn't mention anything about like the accelerating expansion of the universe or anything, but I'm happy to try to talk about that if you'd like as well. So thank you.
Do we have any questions for Malena in the room or on Zoom? I could ask a question about your ground-based observations since it's a topic in the news a lot. Are you getting any interference from all these satellites? Like, has that affected your data at all?
Yeah, so this For the observations that I'm doing, usually they're looking at such a tiny part of the sky that it hasn't been a problem for me personally. I have talked to other astronomers who are less than pleased with the Starlink streaks that go through their images, particularly when you're doing these large scale, wide frame surveys. So if you're doing any types of observations that look at a large fraction of the sky from the ground, then at this point, they usually have Starlink streaks in them. So that's something that particularly for the Vera Rubin Observatory is going to be a big issue. And so they've been sort of looking into ways to use machine learning or something else to try to mitigate the issues from that. But yeah, it's definitely something that people are thinking about, and it's not clear how big a problem that's going to be moving forward because it's not entirely clear how many Starlink satellites will eventually be launched.
Yes, yeah.
Oh, yeah, you mentioned moonlight affected tests.
Mhm.
Where is tests?
Well,
It's out of the atmosphere.
Yeah, so TESS is on this very eccentric orbit around the Earth. So it's outside of the Earth's atmosphere, and it's beyond low Earth orbit, but the moon, depending on where it's oriented relative to the telescope, can still reflect a lot of light into the images that are being taken by the telescope. So this isn't generally too much of a problem, but these are pretty sensitive observations, and so it can be more of an issue depending on where you're looking in the sky. So just to be safe, they try to look in parts of the sky where you're not going to have, or you're going to have as little of an effect from the moon as possible. But it varies a little bit over the orbit. So TESS actually orbits twice for every time, or for every sector. So we saw that it observes each part of the sky for about 30 days at a time, and it orbits twice during that time. So at different points in its orbit, it's at different places relative to the moon. So it's going to change a little bit with time as well.
Yeah, I have a question, and it relates to the issue of the distribution of objects in the Kuiper Belt and maybe in the Oort cloud itself. There was a paper recently in the journal Geology that looked at radioisotopes in zircon crystals from the Pilbara and North Greenland, what do they call them, cratons. And it suggested that there was a 200 million year cycle of small objects bombarding the Earth as comets. And they suggested that had to do something with the Earth, with the solar systems passing and the sun passing through the spiral arms of the Milky Way, which don't rotate at the same rate as the stars. And I wonder whether or not there's some scrambling that takes place even in the larger objects like Planet 9 that you might be looking for, that somehow makes the orbits not as consistently planar as you might think. And part of the problem, if we only see those orbits, is the drunk looking for his keys under the lamppost, as we mostly look at those planes. Now, maybe Vera Rubin will do something about that, but I just wonder whether you think that there are even more external inputs to the issue of orbiting bodies around stars, such as passing through density waves of the Milky Way.
Yeah. Okay, that's interesting that it's thought to be related to density waves in the spiral arms of the Milky Way. So I'm surprised that has a large enough effect to actually see a lot of extra asteroids. But I have not read that paper, so I'm not sure exactly. But it's definitely true that Planet 9 is a very kind of heated controversy back and forth, where some astronomers are pretty adamant that it has to exist. Other astronomers think this absolutely doesn't have to exist, and it's just an observational bias. It's true that we're not sensitive in many surveys to objects that are in roughly the galactic plane, and also the ecliptic plane has a lot of asteroids in it. So the region where Planet 9 is thought to be, and also where a lot of these asteroids on the other sky would have probably been found if they existed, is in this really noisy part of the sky. So it's possible that the reason we haven't found them is just because they're hard to find. They're in a place where there are a lot of point sources. So my survey that I've been working on has been kind of, again, agnostic to what it will find, but should also be sensitive to these extreme trans-Neptunian objects and other things on that side of the sky. So I think a lot of this problem will be hopefully resolved by just seeing, are there other things that are out on that side of the sky, and doing very well characterized surveys that are actually able to say very definitively, we should have seen something but saw nothing, or alternatively, we do find other objects on that side of the sky, and then maybe you don't need a Planet 9 after all. So those are kind of the two possible outcomes, or it's not really clear what else could have produced that orbital clustering other than Planet 9, because you could get a stellar flyby or something that could also push those orbits to one side. But then if you have that, it's actually really unlikely that the star, or that the sun in particular, had a stellar flyby close enough to produce that kind of effect just within the past billion years. And a billion years is the time that it takes for the orbits to spread out. So at this point, the main argument is really, does that clustering exist or does it not? And that's really what's going to kind of define whether or not we need a Planet 9 to explain that.
We have a couple of questions on the chat. So from Joe, the question is there any evidence for or against Planet 9 actually being a very small black hole? Is this a theory your team or other teams have explored?
Yeah, so this is mostly an Occam's razor question, because there have been publications saying maybe Planet 9 is a black hole. I think there was one last week that said it was something related to dark matter potentially. And really the only constraint from any of these models is that it would have to be some body that is about 5 to 10 Earth masses, and it doesn't have to be a planet. It could be anything. The reason that most astronomers tend towards calling it probably a planet is because that is the least unnatural thing to have. It would be extraordinary, and it would be really incredible if it was a black hole, and I'm sure that would teach us a tremendous amount. But following Occam's razor, you usually have to try to assume the most mundane thing unless it is kind of otherwise proven. And so Planet 9, it sounds sort of flashy to us, but if it existed, this is the most common type of planet we've found in other systems. So it's really a relatively mundane solution to this problem if it is there. So it could be a black hole, but I wouldn't bet on it, but it's possible, and we have no way of ruling that out right now.
And then we just have one more, says from Daniel. A lot of the space-based scopes are on the IR side. It helps to see cold dark things. So it says Ceres has a very low albedo. How does space-based IR sensitivity play into very distant object detection? Albedo in those wavelengths, etc.
Yeah, so there has been the WISE survey, which is the wide field infrared explorer, that was, I think it was a little bit lower resolution than TESS, but that was actually used to search the entire sky. There's actually a sort of citizen science effort through the WISE survey where you can go through the data and you can say, does this look like Planet 9? And so far Planet 9 hasn't been found, but citizen scientists have found a lot of brown dwarfs. So those are objects between planets and stars. And that's been really great because brown dwarfs are also really important and useful to understand, and we don't know too much about them. But yeah, it's something that if we could just design our own telescope and launch it specifically to search for Planet 9, maybe that's what it would look like, but a higher resolution version of something like WISE. But yeah, I guess the issue is that a lot of the space-based instruments that do have infrared capabilities like James Webb and a lot of like Hubble, all of these other instruments. Spitzer in the past was, I guess, yeah, Spitzer more so than Hubble was looking in the infrared. They are looking at very small patches of the sky. So what you need is to have really high sensitivity to very dim objects and look over a huge swath of the sky. So things like James Webb are usually used to follow up already known objects and to get much higher precision observations of them, because it has a really tiny field of view and the cameras are designed for very detailed observations of small things or small angular sizes on the sky, at least. Whereas for something like looking for Planet 9, since we don't know where it would be in the sky, you sort of need to have a telescope that is looking everywhere in sufficiently high resolution that you would be able to detect it. So it's sort of a tricky question where a lot of telescopes are optimized one way or the other, where they're either really sensitive to very, very kind of detailed signals, but they only look at a small part of space, or they look at a lot of space, but then they're less sensitive. And so it's a matter of finding the right solution to the specific question, I guess.
Okay, so, we have one more. What about your research is most exciting to you?
Yeah, that's a good question. Yeah, it's tough because so there's like the really high risk, high impact of Planet 9 versus the like it's obviously going to give us an answer type research that I do on looking at exoplanets. And I think I am really excited about exoplanets because we don't know just about anything about them. And I think that's so exciting because there is so much that remains to be discovered, so much that remains to be explored, and it's just this giant playground for understanding planetary systems in general. So, and I think that's a lot of what motivates me for studying Planet 9 as well, is that it's such a strange thing to potentially have, and that the fact that we wouldn't already know whether or not that exists is just really fascinating to me. Where I love kind of wrapping my mind around questions where it's just kind of remarkable how much we still have yet to explore and how much the universe still has to teach us about kind of the world that we live in and what our place is within it. So yeah, I don't know if that was really, it wasn't a very specific answer, but I guess I just love learning about planets and kind of trying to figure out the answers to these really big questions that we still don't even have even like basic answers to, like again, how many planets are in the solar system? Like, what does a typical planetary system look like? And just like, what is a typical planet made of? We still don't really have concrete answers to a lot of these things. And yeah, I just think it's so fun that there are so many weird things out there that we just keep discovering. And yeah, I think it's really exciting to spend my days just kind of poring over, like, why does this exist? That's so strange. I don't understand it. And hopefully someday I will, but it's really interesting that scientists love to not understand things, because that means we have more work to do and we have more to figure out. And it's like a mental playground. So yeah.
Okay, so I'd like to thank you for a fantastic evening.
Yeah. Thank you all.
Okay, I'm gonna close the session. So good night to all our people who are on, and good night to Malena. And actually, I do have one more question, which is how crazy the planetary scientists at MIT, how crazy do they think the guys at Harvard are about Oumuamua?
I think people are pretty tempered about it. Probably because it's like right across town. If you ask my advisor at Yale, he would not hold back. Yeah, but yeah, people try to be nice.
All right. Good night.
Thank you.